Hello, my name is Moses Kolesise, and currently I'm a researcher for the Digital Society School at the Amsterdam University of Applied Sciences. There I work on how do we make the use of generative AI more sustainable, especially taking into consideration the cost of use of generative AI and also the benefit of using generative AI. My background, I have a master's degree in environmental sciences from Wageningen University in research, where I mostly focus on water systems and global change. Before that, I have a bachelor's in geology, and my first master's was in industrial engineering. So I kind of understand that people from different background, how they come into this course. I took this course also last year. And so today we are going to calculate ENSO, the NINO 3.4 anomaly with X-ray. And so an anomaly is mostly something that is deviate or changes from what is normal or standard. So first, what is ENSO? ENSO stands for El Nino Southern Oscillation. And this is a natural cycle or a phenomenon that happens in the tropical Pacific, where there's a swings or changes between warm phases called El Nino and cool phases called La Nina. And climate scientists care much about these changes or these swings because these changes, they don't always stay in the ocean. They also determine rainfall, drought, and extreme weather in the entire globe. And one way climate scientists can track this is with the NINO 3.4 index, where they calculate the NINO 3.4 anomaly. And so here we can see the NINO 3.4 region. So the NINO 3.4 region is between 5 degrees north and 5 degrees south of the equator, and between 170 degrees west and 120 degrees. So that's the NINO region. And so we can go and straight to computing the anomalies. So like I said before, an anomaly is kind of the deviation from what is standard and normal. And an anomaly here, it's like you want to see how a particular month deviate from what is standard for that month. So one way to do that is to take the month, let's say for January 2005, and then we subtract the average mean or the average of all those months, and then we can get the anomaly. And so there are 3 main steps to obtain the anomaly for the NINO 3.4 datasets. And the first is to group by. And the group by method, what it mostly does is it takes all the Januaries and put them in one bucket, all the Februaries in another bucket, and so on and so forth. And then the second is we subtract the mean sea surface temperature from the monthly data. And finally, we can get the anomalies by computing the weighted average. And so here is the code. We then group by, we find the mean. And here we are going to find the ruling mean because we have to smooth out the curve because there might be some outliers. So we want to smooth out the curve so we can see what the original data demonstrate. Then we can go to the month, so we can see here the anomalies in blue, and then the 5-month running mean. And so we can find the standard deviation of these. So our standard deviation is 1.84. We can normalize the data, then we can plot, visualize, and compute the NINO 3.4 index. So we can see here the NINO 3.4 index. So we can see the swings between the red ones, the El Nino, the warm phases, and the blue ones, the La Ninas, the cool phases. And so we can see for example, here in 2002, the event here of this warm phases, and here in 2009. So we can see those warm phases. And so this is the way we can calculate the anomaly, the NINO 3.4 anomaly, and then plot it and see the anomalies across, see both the cool phases and the warm phases.